Hello everyone. So welcome to the next video of the series. So this video will be on process states. Okay. So before I get into the possible states of a process, I would like to tell you one more thing called dispatcher. Okay. So what is dispatcher? Dispatcher is a piece of software that helps in context switching. That we all know. Let's say there is CPU and there is a process P1 is currently getting executed at CPU. Somehow P2 has come. Let's say P2 has higher priority. As a result, this P1 has to be pulled out of CPU and P2 has to be pushed into the CPU. So this is called context switch that we have already seen. So in context switch, whatever progress this P1 has made so far, that has to be stored somewhere. Okay. So this context is stored in this program control block. This program control block is updated and this program control block is saved. Then only this process P1 can be preempted from the CPU and process P2 can be given to the CPU. So this process is this thing is called context switching, and this updating PCB, saving PCB, these things are not easy. These things are not light work. These things are indeed a heavy work. So this context switch and saving the required information, everything, this heavy work is being done by this software called dispatcher. So this dispatcher lifts the heavy work of assigning a process to a CPU. Okay. So this is the main purpose of a dispatcher. Now let's see this state diagram. Okay. So you can see these are the few circles that I have made, and these circles are the different states that a process can be present in. Okay. And these are the transitions among the processes. Fine. So at the very beginning, I will be going to this new phase, new state. This new state is basically the process creation phase. Let's say you have opened your laptop and you have double clicked on the Chrome icon. Now your operating system will get a message that this user wants me to prepare a process out of the chrome.exe file. Okay. Then your operating system will see what are the required resources, and your operating system will start assigning those required resources so that it can gift you a process of this Chrome application. Okay. So this creation phase, during this creation phase, the process stays in the new state. So once this creation phase is over, the process comes into the ready state. What happens in ready state? In ready state, the process is completely ready. The process is staying in the RAM, and the process says, whenever possible, whenever CPU calls me, I am ready to execute. Okay, I don't have any other business. I am just ready for the CPU. Okay, and it stays in the RAM. So at that time, it is called the process in the ready state. So let's say your dispatcher has come, dispatcher has assigned, let's say there is a process P1, your dispatcher has come, dispatcher has taken this process P1 and has assigned this to your CPU, and as a result this process P1 started execution. Okay, the moment process P1 started execution, we will be calling that process P1 is in the run state. So during this ready state and during the run state, in both of the state, the process stays in the RAM. Once the process is done with the execution, the process is getting pushed into the termination phase. Okay, termination as in the process is done, this PCB is deleted, and all the resources are freed up. So now let's see this transition from run state to ready state. So this is a case of preemption. Okay, process is moving from run state to ready state. So this transition takes place in two cases. One is timeout, another one is priority. So what is timeout? Let's say for a operating system, there is something called time quantum value. Let's say for a operating system, time quantum value is 2 seconds. Okay. What is the meaning of having time quantum value is 2 seconds is your operating system will be saying to all the processes in the system, see, hey processes, I don't care how much time you require to get finished. You can never hold the CPU for more than 2 seconds in a continuous way. Okay. So the moment you are holding a CPU for more than 2 seconds, I will come and I will throw you out from the CPU and I will put you in the ready state. Okay. Let's say there is a process which requires 10 seconds to be done. Okay. Right after 2 seconds, your operating system will come and operating system will say, hey process, even though you have 8 more seconds to execute, I don't care. You have already running out of your time. This timeout has happened as 2 seconds is already passed. Okay, so please leave the CPU. and make space for other processes so that those processes can also use the CPU and be in the ready state. Okay, and coming to priority, let's say process 1 is getting executed in the CPU. Let's say process 2 has come with much more higher priority. Your operating system will say, hey process 1, even though you are executing that I can understand, but now process 2 has come in the system, and process 2 has much more higher priority than you, so please leave the CPU, stay in the ready state, and let me run process P2 due to the high priority. Now let's say this transition and this block and wait state, okay, and we'll be seeing this transition as well. So as of now, just consider the IO and ignore this system call operation. Okay, this system call, whatever I have written, just ignore this as of now. let's say let's say you have a process that is P1. Okay, total length is 10 seconds. Fine. So initial 2 second is with CPU, and then 8 second is with IO. Fine, maybe network or some file or something, anything else. Okay, so if the CPU, I mean, if the process P1 keeps the CPU with it for the entire 10 second, so this 8 second, the last 8 second, your CPU will sit idle, your CPU will not be doing anything. Okay, so this is not something that we are expecting. Then operating system will come and say, hey process 1, you are done with the CPU as of now, and right now you are doing some IO operation. Then why you are holding CPU? Please leave the CPU and go to the block state so that other processes now can chance to get the CPU. Okay, by saying this thing, operating system will push this process P1 to the block state. So once this IO is done, this IO operation is done, whatever, maybe file read or write or some network calls, anything. Okay, once this is done, again this process is pushed to the ready state. Okay, now let's see this suspended block state. Okay, so one thing I forgot to mention, during this block state, the process stays in the RAM only. Okay, so let's say there are multiple processes in the RAM which are in the block state. Fine. So as a result, those processes are consuming space in your RAM. So it may happen you are running out of memory. It may happen this. Okay, it may happen that multiple processes are trying to get into the RAM, and RAM is already occupied by those processes which are waiting for the RAM. Now your operating system will come, and operating system will say, hey process, you are doing the IO operation and you are not doing anything else. Given that staying in the disk also you can continue IO, why you are wasting space in the memory? Please go to the disk and staying in the disk, complete the IO, and then they'll let me know. Okay, by saying this thing, your operating system will be pushing some processes from block state to the suspended block state. Okay, let's say in future during the IO operation, somehow your RAM is empty. Okay, your RAM is having sufficient space. Then your CPU may pull some processes from the suspended block to the block state. Fine. And one more thing may happen. Let's say you're staying in the hard disk, your process is done with the IO operation. Okay. Now this can be pushed into this suspended ready state. Fine. So what is suspended ready? So there are two points from which suspended ready can be entered. So one is from suspended block. Once the IO operation is done, okay, then the process is pushed to the suspended ready from suspended block. And one more transition is there from ready to the suspended ready. What happens is, let's say there are multiple processes in the RAM. Okay, fine. Let's say there are 10 processes in the RAM. Let's say there are process 1 to process 10 is in the RAM. Okay, now process 11 has come. Fine. So now we have 11 processes. Okay, but let's say we can accommodate only 10 processes in the RAM. So as a result, one process is extra that we cannot accommodate in the RAM. Now operating system will say, okay, let's say operating system will be picking, let's say, low priority process. Operating system will say, oh, you have the lowest priority, so there is no chance sooner you will be getting CPU time. So don't waste my space in the RAM. Instead of that, stay in the hard disk. Once I have sufficient space, I'll pull you out. Okay, by saying this thing, operating system may push few of the processes into this suspended ready state. And once once the operating system sees some space in the RAM, operating system may pull some process out of the suspended ready to the ready state. Now let's see this thing. So dispatcher takes a process and assigns it to the CPU, that already we have seen. Now comes when RAM is running out of space, non-running processes may get pushed to the secondary memory. That means suspended block and suspended ready, that I already showed you in the above state diagram. Okay, so this thing talks about the suspended state. Okay, suspended state, it might be ready or might be block. Fine. What is swap space? So secondary space, remember, secondary space that operating system uses as extra virtual memory when RAM is full. So when RAM is full, then where these processes are getting pushed into the suspended block or the suspended ready state. So this whatever process is in the suspended block or whatever process is in the suspended ready state, these processes occupy some space in your hard disk, and this space is called swap space. Okay. Now there is something called scheduler. All right. There are three kind of schedulers are there. One is long term scheduler, another one is medium term scheduler, another one is the short term scheduler. Okay, we will be seeing the responsibilities of each of the schedulers. Okay, let me go to the state diagram. This is the state diagram. Okay, so the main responsibility of the long term scheduler is, that is, to create the processes and put the processes in the ready state. Okay, if you come here, responsible for creation of the processes. Okay, let's say your long term scheduler is creating so many CPU processes, only CPU bound processes. So what will happen? Lots of context switches. Okay, all the processes will be, I mean, most of the processes will be waiting for the CPU, lots of context switches. Okay, so as a result, that will be, your performance will be impacted. Okay, and let's say your long term scheduler is creating only those processes which are IO bound. All right, so what will happen? What your CPU will, most of the time your CPU will be staying idle. Okay, you are wasting your CPU time. So that is also, in some aspect, that is also a performance impact. So long term scheduler's responsibility is to create a proper mix of CPU bound and IO bound process, so that your performance is not impacted. Okay, and and that is a point one. And point two is, you are getting a proper CPU utilization. Okay, then comes this medium term scheduler. Okay, so medium term scheduler says, okay, I'll come to this medium term scheduler later. So another thing is short term scheduler. So short term scheduler says which process will run next. So that means your short term scheduler says, which, let's say there are multiple processes in the ready state, P2, P3, P4, like P10. Okay, now short term scheduler says, among these 10 processes, which process has to be run now. Okay, let's say short term scheduler decides, okay, process 5 will be run next. Okay, so short term scheduler says, hey dispatcher, now I have decided this process 5 will be running at the CPU. So please go ahead and do whatever the needful. Okay, so the short term scheduler decides which process will be running next. So the thing is, let's say short term scheduler is not wisely choosing the processes. So what will happen there? It may happen that your system is facing so many context switches. Okay, so with so many context switches, it may happen that your performance is getting impacted really badly. Okay, so the responsibility of short term scheduler is to wisely make decisions, so that you are having these context switches as minimum as possible. Okay, now let's come to this medium term scheduler. What is the responsibility of medium term scheduler? Medium term scheduler's responsibility is this point and this point. Okay, so medium term scheduler decides which processes will be pushed to the suspended block and which processes will be pushed to this suspended ready. Okay, so if this medium term scheduler doesn't decide this wisely, what will happen? Lots of swaps will be there. Okay, lots of disk reads and disk writes will be there. Okay, so then also your performance will get impacted. So the thing is, I mean, the responsibility of this midterm scheduler is wisely pick the processes that has to be put in the swap space, so that end of the day we are having minimum number of disk write and disk reads. Okay, so these are the three types of schedulers and their corresponding responsibilities. Fine.